Hello friends, today we are going to solve Schrodinger wave equation for particle in one-dimensional box. Now suppose a particle of mass m moving in x direction inside a box of length L and height infinite. Now the potential applied outside the box is infinite such that particle remain inside the box only and the potential inside the box is taken as 0 so that the particle is moving only on its kinetic energy, right? So for this system, we can write Schrodinger wave equation as d square xi upon dx square plus 8 pi square m upon h square into e minus v xi is equal to 0. Now potential outside the box is infinite. So substituting this, we get e minus v is equal to minus infinity. Now if we put in this equation 1, we get d square xi upon dx square plus 8 pi square m upon h square into minus infinity xi is equal to 0. We can write this as d square xi upon dx square is equal to 8 pi square m upon h square into infinity into xi is equal to 0. Rearranging this, we get xi is equal to 1 by infinity into h square upon 8 pi square m into d square xi upon dx square. So from here we get xi is equal to 0 as we have infinity in denominator. So we get xi is equal to 0. What does this imply? This implies that xi is 0 everywhere outside this box. Xi is 0 everywhere outside this box. Now inside the box we have v is equal to 0. So if we put v is equal to 0 in Schrodinger wave equation, we get d square xi upon dx square plus 8 pi square m upon h square into e to xi is equal to 0. Now in order to homogenize this equation, we take 8 pi square m upon h square e is equal to alpha square. Substituting this, we get d square xi upon dx square plus alpha square xi is equal to 0. Now this is a differential equation of order 2. This is a differential equation of order 2. So solution of this equation, solution of this equation is xi is equal to a sin alpha x plus b cos alpha x, right? Now we have to find the value of a and b. For this we will apply the boundary condition. Now applying the first boundary condition, that is xi is equal to 0 at x is equal to 0. At x is equal to 0, outside the box v is outside the box, xi is 0. So we can write 0 is equal to a sine alpha into 0 plus b cos alpha into 0. Now this value is 0, right? So we can write b cos 0 is equal to 0. Now cos 0 is 1, so b must be 0. This implies that b is equal to 0, right? So our equation reduces to xi is equal to a sine alpha x. Now we have xi is equal to a sine alpha x plus b cos alpha x. Now b is equal to 0, so our equation reduces to a sine alpha x. Xi is equal to a sine alpha x. Now we will apply second boundary condition. What is this? Xi is equal to 0 at x is equal to L, right? At x is equal to L, xi is equal to 0, because we saw that if we take potential infinite, we get xi is equal to 0. So at x is equal to L, we have infinite potential, that's why xi is equal to 0. Now this implies that a sine alpha x is equal to 0 at x is equal to a sine alpha x, or a sine alpha L is equal to 0 at x is equal to L. Now since a cannot be equal to 0, otherwise whole equation will turn out to be 0. So only possibility is sine alpha L is equal to 0. Sine alpha L is equal to 0. This implies that alpha L is equal to n pi. Alpha L is equal to n pi, or alpha is equal to n pi by L. Now if we substitute the value of alpha, if we substitute this value of alpha is equal to n pi by L in this equation, we get xi is equal to a sine n pi by L into x, right? Now we have to find the value of a. To find the value of a, we will normalize this equation. So first we will see what is normalization. Normalization is defined as total space probability must be 1, and mathematically it is represented as integral of xi n into xi n star dou tau space is equal to 1. Dou tau space is equal to 1, right? So in order to normalize this equation, xi n is equal to a sine n pi by L into x. We will take it as integral xi n square dx from 0 to L is equal to 1. Since the length of box is L, so we will take integral 0 to L. Now we will put the value of xi n 0 to L. A a square sine square n pi upon L into x dx is equal to 1. Solving this, we get a square integral 0 to L half 1 minus cos of 2n pi by L, 2n pi by L into x dx is equal to 1. So how did we get this? Since cos 2x is equal to 1 minus 2 sine square x. So we have substituted the value of sine square x, we get this equation. Now separating this, we get a square by 2 integral 0 to L dx minus a square by 2 integral 0 to L cos of 2n pi by L into x dx is equal to 1, right? Solving this, we get a square by 2 L minus 0. After integrating this, the value of cos 2n pi by L into x 0 to L will be turn out to be 0. So this become a square by 2 L minus 0 is equal to 1, or a square is equal to 2 by L. This implies that a is equal to root 2 by L, right? A is equal to root 2 by L, and hence we can write psi n is equal to root 2 by L sine root 2 by L sine n pi by x, n pi by L into x. So this is normalized wave function. This is normalized wave function. Now one more thing we have left is, now earlier by solving we got alpha is equal to n pi by L. After applying the boundary condition, we got alpha is equal to n pi by L, and we have considered, if you remember, we have considered alpha square is equal to 8 pi square m upon h square into E. So now, so if we look at this, alpha is equal to n pi by L, and we have considered alpha square is equal to 8 pi square m into En upon h square, right? So n square pi square upon L square, combining this with this, we get n square pi square L square is equal to 8 pi square m En upon h square, right? From here we get En is equal to n square h square upon 8 ml square, n square h square upon 8 ml square. This is energy of particle inside box. This is energy of particle inside box. So that's it for today.